This lecture is about the inverted index construction. In this lecture, we will continue the discussion of system implementation. In particular, we're going to discuss how to construct the inverted index. The construction of the inverted index is actually very easy if the data set is very small. It's very easy to construct a dictionary and then store the postings in a file. The problem is that when our data is not able to fit to the memory, then we have to use some special method to deal with it. Right? And unfortunately, in most retrieval applications, the data set would be large and they generally cannot be loaded into the memory at once. And there are many approaches to solving that problem. And sorting-based method is quite common. It works in 4 steps, as shown here. First, you collect the local term ID, document ID, and frequency tuples. Basically, you're going to count the terms in a small set of documents, right? And then once you collect those counts, you can sort those counts based on terms so that you build a local, a partial inverted index. And these are called rounds. And then you write them into a temporary file on the disk. And then you merge in step 3, you would do pairwise merging of these rounds until you eventually merge all the rounds to generate a single inverted index. So this is an illustration of this method. On the left, you see some documents. And on the right, we have shown a term lexicon and a document ID lexicon. And these lexicons are to map string-based representations of document IDs or terms into integer representations, and map back from integers to the string representation. And the reason why we are interested in using integers to represent these IDs is because integers are often easier to handle. For example, integers can be used as index for array, and they are also easy to compress. And so this is one reason why we tend to map these strings into integers, so that we don't have to carry these strings around. So how does this approach work? Well, it's very simple. We're going to scan these documents sequentially and then parse the documents and count the frequencies of terms. And in this stage, we generally sort the frequencies by document IDs because we process each document sequentially. So we first count all the terms in the first document. Therefore, the document IDs are all ones in this case. Right? So, and this will be followed by document IDs tools. And they are naturally sorted in this order just because we process the data in the sequential order. At some point, we will run out of memory, and then we would have to write them into the disk. Before we do that, we're going to sort them. Just use whatever memory we have, we can sort them, and then this time we're going to sort based on term IDs. Note that here we're using the term IDs as a key to sort. So all the entries that share the same term would be grouped together. In this case, we can see all the IDs of documents that match term 1 would be grouped together. And we're going to write this into the disk as a temporary file. And that would allow us to use the memory to process the next batch of documents. And we're going to do that for all the documents. So we're going to write a lot of temporary files into the disk. And then the next stage is to do merge sort. Basically, we're going to merge them and then sort them. Eventually, we will get a single inverted index where their entries are sorted based on term IDs. And on the top, we can see these are all the entries for the documents that match term ID 1. So this is basically how we can do the construction of inverted index, even though the data cannot be or loaded into the memory. Now, we mentioned earlier that because the postings are very large, it's desirable to compress them. So let's now talk a little bit about how we compress inverted index. Well, the idea of compression in general is to leverage skewed distributions of values. And we generally have to use variable length encoding instead of the fixed length encoding as we use by default in a programming language like C++. And so how can we leverage the skewed distributions of values to compress these values? Well, in general, we would use fewer bits to encode those frequent words at the cost of using longer bits to encode those rare values. So in our case, let's think about how we can compress the TF, term frequency. Now, if you can picture what the inverted index would look like, and you'll see in postings there are a lot of term frequencies. Those are the frequencies of terms in all those documents. Now, if you think about what kind of values are most frequent there, you probably will be able to guess that small numbers tend to occur far more frequently than large numbers. Why? Well, think about the distribution of words, and this is due to the Zipf's law, and many words occur just rarely. So we see a lot of small numbers. Therefore, we can use fewer bits for the small but highly frequent integers, and at the cost of using more bits for large integers. This is a trade-off, of course. If the values are distributed uniformly, then this won't save us any space. But because we tend to see many small values, they are very frequent, we can save on average, even though sometimes when we see a large number, we have to use a lot of bits. What about the document IDs that we also saw in postings? Well, they are not distributed in a skewed way, right? So how can we deal with that? Well, it turns out that you can use a trick called a dgap, and that is to store the difference of these term IDs. And we can imagine if a term has matched many documents, then there will be a long list of document IDs. So when we take the gap and when we take the difference between adjacent document IDs, those gaps will be small. So we will again see a lot of small numbers. Whereas if a term occurred in only a few documents, then the gap would be large. The large numbers will not be frequent. So this creates some skewed distribution that would allow us to compress these values. And this is also possible because in order to uncover or uncompress these document IDs, we have to sequentially process the data because we store the difference. And in order to recover the exact document ID, we have to first recover the previous document ID, and then we can add the difference to the previous document ID to restore the current document ID. Now, this is possible because we only need to have sequential access to those document IDs. Once we look up a term, we fetch all the document IDs that match the term, then we sequentially process them. So it's very natural. That's why this trick actually works. And there are many different methods for encoding. So binary code is a commonly used code in just any program language where we use basically fixed length encoding. Unary code and gamma code and delta code are all possibilities, and there are many other possibilities. So let's look at some of them in more detail. Binary coding is really equal length encoding, and that's appropriate for randomly distributed values. The unary coding is a variable length encoding method. In this case, an integer that's at least 1 would be encoded as x minus 1 bits followed by 0. So for example, 3 would be encoded as 2 ones followed by 0, whereas 5 would be encoded as 4 ones followed by 0, etc. So now you can imagine how many bits do we have to use for a large number like 100. So how many bits do we have to use exactly for a number like 100? Well, exactly we have to use 100 bits, right? So it's the same number of bits as the value of this number. So this is very inefficient if you will likely see some large numbers. Imagine if you occasionally see a number like 1000, you have to use 1000 bits. So this only works well if you are absolutely sure that there will be no large numbers. Mostly very often you see very small numbers. Now, how do you decode this code? Since these are variable length encoding methods, and you can't just count how many bits and then just stop, right? And you can say 8 bits or 32 bits, then you will start another code. They are variable lengths, so you have to rely on some mechanism. In this case, for unary, you can see it's very easy to see the boundary. Now you can easily see 0 would signal the end of encoding. So you just count how many ones you have seen, and then until you hit the 0, you know you have finished one number. You will start another number. Now, we just saw that unary coding is too aggressive in rewarding small numbers. And if you occasionally can see a very big number, it will be a disaster. So what about some other less aggressive method? Well, gamma coding is one of them. And in this method, we're going to use unary coding for a transformed form of the value. So it's 1 plus the floor of log of x. So the magnitude of this value is much lower than the original x. So that's why we can afford using unary code for that. So we'll first have the unary code for coding this log of x. And this will be followed by a uniform code or binary code. And this is basically the same. Uniform code and binary code are the same. And we're going to use this code to code the remaining part of the value of x. And this is basically precise x minus 1 to the floor of log of x. So the unary code basically code the floor of log of x. Well, add 1 there, like here. But the remaining part will be using uniform code to actually code the difference between the x and this 2 to the log of x. And it's easy to show that for this value, this difference, we only need to use up to this many bits and the floor of log of x bits. And this is easy to understand. If the difference is too large, then we would have a higher floor of log of x. So here are some examples. For example, 3 is encoded as 101. The first 2 digits are the unary code. Right? So this is for the value 2. Right? 10 encodes 2 in unary coding. And so that means log of x, the floor of log of x is 1, because we want to actually use unary code to encode 1 plus the floor of log of x. Since this is 2, then we know that the floor of log of x is actually 1. So, but 3 is still larger than 2 to the 1. So the difference is 1, and that 1 is encoded here at the end. So that's why we have 101 for 3. Now, similarly, 5 is encoded as 110 followed by 01. And in this case, the unary code encodes 3. And so this is the unary code, 110. And so the floor of log of x is 2. And that means we're going to compute the difference between 5 and 2 to the 2. And that's 1. And so we now have, again, 1 at the end. But this time we're going to use 2 bits, because with this level of floor of log of x, we could have more numbers, 5, 6, 7. They would all share the same prefix here, 110. So in order to differentiate them, we have to use 2 bits in the end to differentiate them. So you can imagine 6 would be 10 here in the end instead of 01 after 110. It's also true that the form of a gamma code is always well, first odd number of bits, and in the center there is a 0. That's the end of the unary code. And before that, on the left side of this 0, there will be all ones. And on the right side of this 0, it's binary coding or uniform coding. So how can you decode such a code? Well, you again first do unary coding, right? Once you hit 0, you know you have got the unary code. And this also will tell you how many bits you have to read further to decode the uniform code. So this is how you can decode the gamma code. There is also delta code that's basically the same as gamma code, except that you replace the unary prefix with the gamma code. So that's even less conservative than gamma code in terms of rewarding the small integers. So that means it's okay if you occasionally see a large number. It's okay with delta code. It's also fine with gamma code. It's really a big loss for unary code, and they are all operating, of course, at different degrees of favoring favoring small integers, and that also means they would be appropriate for a certain distribution, but none of them is perfect for all distributions. And which method works the best would have to depend on the actual distribution in your data set. For inverted index compression, people have found that gamma coding seems to work well. So how do we uncompress inverted index? We just talked about this. First, you decode those encoded integers, and we just, I think, discussed how we decode unary coding and gamma coding. So I won't repeat. What about the document IDs that might be compressed using dgap? Well, we're going to do sequential decoding. So suppose the encoded ID list is x1, x2, x3, etc. We first decode x1 to obtain the first document ID, ID1. Then we would decode x2, which is actually the difference between the second ID and the first one. So we have to add the decoded value of x2 to ID1 to recover the value of the ID at this second position, right? So this is where you can see the advantage of converting document IDs into integers, and that allows us to do this kind of compression. And we just repeat until we decode all the documents. Every time we use the document ID in the previous position to help recover the document ID in the next position.